Today, we are starting our next unit on polynomials. And so if we wrote out an equation like this, y equals 3x, this equation here, y equals 3x minus 5, what kind of equation is this in general? What do you think? Close. Technically, yes, because it has two components, a binomial. But is it like, but if we looked at this equation and we like set on a graph, oh, this is the trend it has, what do you think? It's linear, right? Because it's just some kind of line. And so this is a linear equation here. If I had something that was y equals x squared plus 5, what kind of equation is that? That one was linear. What's this one? Yes, it's nonlinear. But this is like a specific type. We just learned about this. It is quadratic. What if it was y equals x cubed plus 3x plus 5? What would we call that? How would you say this? X to the third power, which is another way of saying x to the third power is x cubed. So it is a cubic function, right? All three of these, and if we kept on going, say like x to the fourth power, x to the fifth power, and on and on and on, all of them fit into a category called polynomials, all right? So that's basically what polynomials are. There are examples of things that are polynomials and aren't polynomials. So if you look on this page here, on this example here, about half of them are polynomials and the other half are not, right? So if we looked, for example, at this first one right here, how could we first simplify this so that this is two separate terms instead of all being just one large term? If you're not quite sure, turn and talk with a neighbor. How could you just separate this? What would one of the terms be? Just one of the terms. What do you think it would be? 4x to the negative 1. So you got that from this first part here. So you did 4 over x, which is the same thing as 4x to the negative 1. And then what about that second term? X squared. Because x cubed divided by x is just x squared. If you have some kind of power that is negative, that is not a polynomial, right? So this one here is not a polynomial. Let's look at number 4 then. Number 4 is just the cubic root of x, the cubed root of x. How could we rewrite that so that it's x to the power of something? 1/3, right? So this is just x to the 1/3. If you have a power that is a fraction, it's not a whole number, it is not a polynomial. So this is also not a polynomial, right? Now look at this second one here, or the number 2. See if you can determine by yourself, is this a polynomial or not? All right, I'll give you a few moments to do so. What do we think? Show of hands, who thinks it's a polynomial? Who thinks it's not a polynomial? All right, looks like we have a consensus. This one is a polynomial. What can you factor out here? You can factor out an x, right? So if you had x times 4 plus x squared over x can cancel out the x's, and you're just left with 4 plus x squared, which is a polynomial. Tricky question. Is 0 a polynomial? Who thinks yes? Who thinks no? All right. If I rewrote 0 as 0 times x to the 0 power, what's x to the 0 power? 1. What's 1 times 0? 0. So can I just add that on, or multiply that on? Will that change anything about it? No. Is 0 a negative number? Is it a fraction? It's neither. Therefore, this is actually a polynomial. All right? 0 is indeed a polynomial. All right. Today, I'm going to be going through a few vocabulary words that I think are going to be important for us for the rest of this unit. Okay? There are 4 that we're going to talk about right now, and then there are a few more later. But the ones that I want to look at right now are degree, leading term, leading coefficient, and constant term. Okay? So, of these, you will already know one of them. Constant term is just another way of saying the constant in your equation, the one that has no x's associated with it, right? So in this first problem here, what is our constant term? It's just -5, all right? What about in this number 3 right here? Do we have a leading term that's evident automatically? We might need to rearrange it. How could we rearrange this fraction? Well, there's going to be a 4, and there's going to be some kind of minus, and there's going to be an x. What else do we have to add? They're all over 5. Both of them. So of these, which one would be our constant term? Right there. Great. Now let's look at this one. This one is just a lot of multiplication altogether, right? But we're looking for the constant term, right? If you had x plus 3 and 3x plus 5, what 2 components would you multiply together to get just the constant? The last 2, right? The numbers. It works the same way here. You just have the numbers, all right? So if we want these numbers multiplied together, we have -1, and see that it's to the 3rd power. So that means that we have -1 to the 3rd power times -2 times 2. And what does that give us? Let's see, -1 to the 3rd power is -1. That's -2, that's 2. So we just get +4. That would be our constant term. What's our constant term for this one? Just 0. There's nothing that's not associated with x, so it's just 0. All right. The next one I want to look at is degree. All degree means is for all of the different powers that you have in your equation. This one is x to the 5th, x to the 2nd, x to the 1st, right? Which one's the largest? And that's all the degree is just the largest one, right? So in this first one, the largest one is just x to the 5th. So your degree is 5. If we look at the 4th one here, how could we find the degree of the 4th one? Is it just x to the 1st? No, it's not, because we need to multiply all of the x values together, right? So if we multiply all the x values together, how many x's are there total? There's x to the 3rd times an x times an x, just multiplying all the x's. So this gives us x to the 5th. So what's our degree? Still 5. Our leading term then is just the entire term that has the degree in it. So for this first example, we know the degree is 5. So this right here is the leading term. It would be the entire thing. So it would be 4x to the 5th. On the other hand, the leading coefficient, what is a coefficient? It's just the number before the variable, right? So the leading coefficient is just the number of our leading term. So in the case of this first problem here, our leading coefficient is just the 4. If we are looking for the leading term in this fourth one here, we don't quite have the leading term yet, right? We need to be able to multiply out all the aspects of the leading term. So now, instead of just looking at the x's, we want to look at the coefficients with the x's on these components. Plus 2. So we have the quantity 2x cubed. We have an x, and we have a 3x. If you multiply that all together, you'll get 8x cubed times 3x squared, which is just 24x to the 5th. So this right here is our leading term. So then what would the leading coefficient be? 24. Okay. Great. Now we're going to talk about end behaviors. How many of you have heard of the term end behavior before? Just like vaguely, sometime in math, maybe once upon a time. All right, end behaviors have to do with our graphs, and it's how our graphs behave at their ends. Okay? Nice way of putting it. So, for example, if I had a graph and an equation that was y equals x squared minus 1, what would my graph look like? Be a parabola. Where would it would start with -1, right? And then would it be going upwards or downwards? Upwards. So it would look like this. Okay. What would I have to change in order to make the parabola face downwards? I have to put a negative right here, and then this would become a downward facing parabola. These right here are the end behaviors. Okay? So if you see this green A, what is that called in terms of the vocab we just learned? It is our leading coefficient. What is the n called? The degree. Yep. So our leading coefficient is positive. So if this was just x squared, our leading coefficient would just be 1, basically, right? So 1 is positive. And if our degree was even, if we have a quadratic, 2 is even, what would your end behavior look like? What does it look like here? It looks like this, right? They're both pointing up. So our end behavior here are just 2 arrows pointing up at the end. What would your end behavior look like if it was a negative leading coefficient? arrows down. Great. Now, you guys have worked with cubic functions before, correct? Do you know what the general shape of a cubic function looks like? Just kind of show it with your hands. It's like, woo, just kind of like a snake squiggle thing. So if I drew this is like a typical cubic function, right? And I said that this was y equals 2x cubed plus 3x plus 1. I don't really have a square term in there, but it doesn't really matter at this point. This, what do my end behaviors look like for this graph? They're opposite, right? So there's one here and there's one here. And so our degree is odd now, but it's still positive. And so because it's positive and it's odd, our end behavior is going to end up with the left arrow pointing down and the right arrow pointing up. If we change this so that this is now negative, what would we have to change about our graph? You just flip it over the x-axis, right? So this would just look kind of like that. And now our end behavior is different again. So now instead of going down on the left, it's going upwards on the left, and it's going downwards on the right. If you want, you can remember this as like a dance. I'm not going to make you guys do that, okay? But these end behaviors are really important to know, because if you are graphing some kind of polynomial and you have no idea how to factor your polynomial, you'll be able to get a pretty good approximation of what it should look like just based off of what the end behaviors are, right? If you have something that's second degree, that's just quadratic. If you have something that's third degree, that's cubic. If you have something that's fourth degree, it's called quartic. Draw a graph of what you think will happen for the second degree and third degree, and then try one out for the fourth degree as well, right? Draw what you think a typical graph would look like for each of these cases. And I'll give you a few moments to do so. So what we are looking at with these different graphs right now is something called extrema and then zeros. What's another word for zeros? What was it? Roots, x-intercepts, solutions, right? Got all those lists of them, right? So based off of these graphs, I think we could figure out what the zeros are pretty easily. So for example, for second degree, how many zeros can you have? You can have 2. Can you have 1? If you drew a parabola like this that just touches once, you can have 1. Can you have 0? You could. You have a parabola like this. So you can have 0, 1, or 2 roots. What about for a third degree? How many times does this one pass through the x-intercept, or the x-axis? Like once, right? If we drew a typical cubic, how many times does that one pass through? 3 times? What about 2? Can we have 2 zeros? Someone last period said, well, what if you did something like this, where you just had it kind of touch like that? Would that be considered 2? So you can have 1, 2, or 3. But the problem here with this 2 is that, is it really 2 roots there? Yeah, it is. Sorry, trying to trick you. All right, then for this last one over here, Fourth degree. What is one way that we could draw something to the fourth degree? Have you ever seen like this kind of W shape? That's a fourth degree, right? So if this is a fourth degree here, and we're looking at the number of zeros here, how many zeros can you count from this one? 4 zeros. That makes sense. All right, what if I moved this so that it looked like this instead? Then how many zeros does it have? Right? Do you think we can get 1, 2, and 3 as well? Maybe, right? Here's a trick. This isn't the only way that you can write something that's quartic, or draw something that's quartic, rather. If you drew a parabola can also represent a quartic function. So some quartic functions just look like a parabola, right? So this one, in this case, you can find that it has 1 or 2 zeros, just by it being a parabola, right? And then, let's see, how could we do 3? What if we did something like, let's see. That. So it crosses here and here, but then it just touches here. Then you can have 3 roots, right? All right. Now the idea of extrema. Extrema is just another way of saying what are the local maximum and minimum. All right. So just looking at our different parabolas in the second degree section here, how many extrema do we have? It's just 1. And depending on whether it's the parabola is facing downwards, upwards, it's a maximum or a minimum. All right. How many extrema could we have here, though? So if we look at this blue graph for the third degree, we have kind of like 2 hills. So you have 2 extrema. But then the original example that we have here, are there any extrema there? Not really, right? It just kind of all curves out. So you can have 0 extrema in that case. And then finally, for this case over here, you could have 1 extrema, right, if it's a parabola. If it's this W-shaped, you can have 3 extrema. Do you think there's a way that you can get 2 or 4 extrema? No. So, in terms of extrema, a parabola only has 1. Your third degree basically has just even numbers of extrema. And your fourth degree only has odd numbers of extrema. Right? If we put all of this together, and if you look at something that's like this function to the 5th power, you don't have to freak out about, oh my gosh, I'm never going to be able to draw this. Because now you can draw it, right? If we have this function here, what components of this are important for us? The exponent. Which exponent in particular? 5 there. And so what does this 5 represent? What does this 5 represent? Yes. And so this is our degree, 5, and it'll help us determine the direction of our graph. What else do we need? Yeah, Bernie? Yep, so this leading number right here, is it positive or negative? It's positive in this case, right? So that is our leading coefficient right there. And then what other piece of information might we need? What was one of our other vocabulary terms? Our constant term, right? Why would our constant term of -5 be important to us? our y-intercept? So if I know that this is -5, I know that it starts down here at -5, or that it has to go through that point at some time, right? So let's see, degree of 5, that's odd. Leading coefficient is positive. So what will our end behaviors look like? Like this? All right. So our end behaviors will look like that. And so if we just draw this, let's see, if it's a degree of 5 means you'll probably have something that's like this-ish. So I'm just going to go like this. It doesn't have to be exact. It's just an approximate right now. So all we need to know about it is that it is degree 5. Our end behavior matches up with what we expect. And it goes through our y-intercept. Right? Now, take a few moments. Try the second one on your own. All right? I'll give you a few moments to do so. Someone from row 1, tell me one important piece of information we need. One important piece of information that we need from this equation. The what? 5. 5 is equal to what? The degree? Okay, so we have a degree of 5. How did you get a degree of 5? So you just looked at those x's. Okay? All right, we have the degree. What other piece of information do we need? Someone from the second row. The leading coefficient. What is our leading coefficient in this case? 24. Some of you may have noticed we already solved all the components of this problem earlier. Yeah? All right. And then what is the final piece of information we need? Our constant term. What does that equal to? Here. 4. Right? So we have a constant term of 4. That means that we're going to cross our y-axis at 4. All right? Degree of 5, positive leading coefficient. We're going to have the same end behavior. Yes? So if we're having the same end behavior, it's still a degree 5, so it still will have the same kind of shape as this graph does. So I'm just going to draw it like this and call it good. Right? Okay. One last thing. This is from an equation, can we get the graph? What if we were asked from information, get the equation? Right? This is going to be important, especially if we're looking at word problems later, right? So for this, we want a polynomial that has zeros at 0.52 and -0.5. So take a few moments, see if you can find or figure out an equation just by looking at this information right here. We don't have to worry about this yet. We'll worry about that later. But if we're looking at just our zeros, we're going to have some kind of equation that starts with y equals. And if we have something with zeros, or roots, or x-intercepts, one of your components, for example, if I said, oh, I know 0 of 2 is just x minus 2, what would my other two components be? Take a few moments, try and figure that out. Okay? I'll pause while you do so. If I went and solved this the same way I did with a 0 of 2. And said, oh, if I have a 0 of 0.5, that's just x minus 0.5. Is this right? Technically, yes, right? It gives us the information we need. However, if you saw this in a typical equation, wouldn't you freak out? Oh my gosh, there are decimals. Why are there decimals? Right? So how could we write this in a way that's not with decimals? Use a 2. So let's get to that point. So I saw some people said, oh, well, you could just write it as a fraction, right? That's what some people last period said. They were like, why don't you just write it as a fraction instead? Except if you saw a fraction in an equation, wouldn't you freak out still? I would, right? I don't like fractions, I don't like decimals, right? So, as Ryan said, if you write this as 2x minus 1, why is that equivalent? Exactly. So, right here, all we did is just said, multiply this by 2, multiply this side by 2. Now both of those sides have been multiplied by 2. We have a 2x minus 1. And if you notice, to find zeros, you just set that component equal to 0. If you set 2x minus 1 equal to 0, you'll still get x equals half. Right? So, if this is 2x minus 1 here, this was our positive 0.5. So then our negative 0.5 will just be the same thing but with a plus. Right? Now, our last problem, we want a leading coefficient of 8, right? If we want a leading coefficient of 8, if we look right now at what we currently have, we have a 2x times an x times a 2x. What does that give us in terms of a leading coefficient? It's just 4, right? So if it's just 4, we need another multiple of 2 to multiply by. So, technically, if I wanted another multiple of 2, where could I put it? Can I just stick one up front? There, I got a 2. Multiplied by another 2, there, I got 8. That works, right? And so from here, if I wanted to graph this out, and I said, all right, this is, what degree is this? There are 3 x's, so that's a degree of 3. We have a positive leading coefficient of 8 now. And so positive, odd degree, it'll still have this trend of down and up. So it'll look something kind of like this. Right? Except moved over a little bit, right? So that we get our roots. Something like that. Okay. Is there another way? There is another way that we can do this, though. Instead of saying, let's put a 2 in front, what if we just changed the degrees? How could we change the degrees of one of these factors so that we get 8 for our leading coefficient? We just need another factor of 2, right? If we need another factor of 2, well, we have a factor of 2 here, right? If we have a factor of 2 here and we need to make it another factor of 2, we should just get another one of those, right? So why don't we just square that one? Yeah. Yes. So, do we have, well, okay, let's put it this way. If we just squared this one, will we have any kind of zeros other than 1/2, 2, and negative 1/2? No. We will have 2 at 1/2. We'll have 2 components at 1/2. But that's still at 1/2. So it's still at the same root. Okay? So if it's at the same root, then in this case here, what we can say about this is that while these two are completely different functions, they're completely different polynomials, right? If you look at this, this is x squared, x and x. You have a degree of 4 now, but you still meet all of the requirements that are written up here. So you can have more than one different answer, all right? And so in terms of this one, you would get, let's see, you would still have 8, so it's still a positive leading coefficient. You have a degree of 4. So if you have a degree of 4, that means that your end behavior is both going to be up. So then here, you'd end up having something that looks kind of like this, right? Same question, 2 different answers that you can get, right? There's not just one way of doing it anymore. All right. If you turn to the next page, I will tell you which homework assignments you can skip, or which homework problems you can skip, right? So, for this first page, just skip the middle one. I don't think you guys need to work with pi's and square roots of 3. I think that's okay. On the second page, let's just skip the last one, since that's typically the hardest one. I don't want you guys to have to do too much work. Let's skip this problem overall. I object to porta boys. All right, and then we already did C. That's the one we just did. So how about you try just A for 6? And then you don't have to do 7. Right? That is all for today. If you want to get started on your homework, you have a few minutes left.